Hello, everyone. Today we're going to tackle problem number 8, which is calculate the inverse of a 2 by 2 matrix. We're going to get as an input a list of lists, which represents a matrix in Python, and then as an output, we're going to return the inverse of this matrix. As is tradition, first I'll start with the intuition behind what it is that we're doing. Afterwards, I'll talk a little bit about the naive solution, which is basically just coding up what's happening underneath the hood from the intuition. And then I'll give you the NumPy one-liner, which is what you will most likely than not use during your project. So without any further ado, let's just dive right. When thinking about inversing a matrix, it is useful to first look at the formula and then start thinking about what it means. And I'll give you two explanations. One is the more math-oriented, the other is a bit more geometrical. For me, the first one is more intuitive, but because I know that some people really like the other explanation, I'll try to talk about it a little bit first. Also, this video is not going to be a full class in linear algebra. I'm going to assume that you know about matrix multiplication. If not, there's a lot of great resources to look into. But the reason why I'm not going too deep into this because this could be a whole lecture just talking about the inverse of a matrix and what it means and why is it possible and what this formula comes from. I'll give you just the little hints that are necessary to get some intuition about how things are going. I highly encourage you to go look at another source if you want to go delve deeper into it, but don't be afraid to ask in the comments for clarification on certain stuff because I have to hand wave some things away because if not, then just recording this whole thing is going to take an hour. So with that out of the way, let's look at the way to inverse a matrix. Or rather, let's think about first what it means to inverse a matrix. And I always like to, when I'm thinking about matrices, which, you know, they have multiple dimensions and they're scary, I like to think about what would happen in the scalar case. So when you're thinking about inverting a number, what you're basically saying is which number multiplied by my original number is going to be equal to 1. So for example, for number 2, we're solving this equation. 2 times x equals 1. And we know that we can solve it by saying x equals 1 over 2, which is 0.5. So that's something that's straightforward. It's very useful when you're working with scalar numbers. And so it's natural to say, well, if you can add, subtract, and multiply matrices, can you divide them? And the answer is kind of. This is not exactly a division, but it's going to work like one. So the idea is that when you have matrix A and you multiply it by matrix, the inverse of matrix A, which is written as A to the minus 1, we're going to get the identity matrix. And in case you forgot, the identity matrix is a matrix in which every element is 0 except for the diagonal, and the diagonals are going to be equal to 1. So this is the identity matrix of a 2 by 2 matrix, but there's also in 3 by 3, 4 by 4, and so on and so forth. So if you have this original matrix A here, the inverse is going to come from this definition, where you're going to have something called here the determinant, and you're going to have to rearrange the elements of the matrix in a specific way. And also we have a caveat that the determinant cannot be 0. But what does that mean, and how do we even get to that? So let's start thinking about one of the ways to interpret linear algebra, which is you're thinking about matrices and you're trying to solve equations with them. So for example, if you remember from your linear algebra classes, there's something called the augmented matrix. So for example, we had A, B, C, and D, and we had this on the right side. We would be solving an equation basically where A times X, which is our unknown, plus B times another unknown, which is y, is going to equal 1. And then we're going to have the same thing for the other row. So all of the rows are just going to be a collection of equations. And we're going to solve to find the values of x and y such that this thing equals 2. And we're going to use a similar idea when trying to find the inverse of the matrix, because we know from definition that a matrix multiplied by its inverse has to equal to the identity matrix. So let's go and dive right in by doing that. So if we have our original matrix A and we multiply it by another matrix, I'm just going to put a prime on all of the elements here just to indicate that they come from another matrix. We want this thing to be equal to the identity matrix. And this one, in case you haven't noticed, this is A, and this is going to be A to the -1, and this is going to be the identity matrix. So now, this, as I said, is just solving an equation, because if you look at it, A is 2 by 2, A to the -1 is 2 by 2, and the identity matrix is 2 by 2. So basically what we're saying is that once we multiply these two matrices, we want the elements to be such that they solve the equation. So the result of the multiplication and the first element has to equal 1, the second element has to equal 0, third has to equal 0, and the fourth has to equal 0. So writing that explicitly, and this is going to be a mouthful, but bear with me, because if it hasn't clicked yet, I assure you it's going to click by now. We're going to multiply this thing. If you know how to multiply a matrix, this is going to be somewhat straightforward. We're going to have A times A prime plus B times C prime in the first element, and then we're going to have A times B prime plus B times D prime. Sorry, this is going to take me a while, so let me just write the other ones that are already pre-computed. And here we go. So what we have here is a system of equations, basically. Or rather, we just have a lot of equations. So we're just saying that this element, the first element has to equal 1, the second has to equal 0, and so on and so forth. So this just reduces to a combination of equations. So A plus A prime plus B C prime equals 1. I'm just rewriting this so it looks more intuitive in case you haven't done it. And please excuse my handwriting, but I suppose you're getting the gist of it right now. This thing, and then finally A, B plus C, D equals 1. So when we're inverting a matrix, the only thing we're doing is we're just solving a system of equations. That's all. And what do we know? Or rather, you would be thinking, hey, but hold on, we're going to have 4 equations. How many unknowns do we have? Well, all of the unknowns are the things with a prime, right? A prime, B prime, C prime, D prime, because those are the elements from the matrix we're trying to calculate. A, B, C, and D are known values because those are from the matrix that we already had, the one that we're looking at. So we have 4 unknowns, we have 4 equations. If you remember from your linear algebra classes, that means that we can solve the system of equations. Now, I could try and solve it here, but with my handwriting and time constraints, this video is going to end up being too long. So let me just tell you that the way of solving this equation, rather the solution, is going to, if there is one, and we're going to talk about that in a bit, is that A prime is going to be equal to D, B prime is going to be equals to minus B, C prime is going to be equal to minus C, and D prime is going to be equal to A. Well, and all of that is going to be divided by a number, but I'm going to call it a square right now. You're going to see why I'm doing this in a second. So there you go. We have a system of equations, and in theory, we can solve it, right? And if we solve it, we're going to get to this thing. But here's the little catch. As I said, all of the elements in the matrix are being divided by a square, right? And what is this square? Well, we can prove that that squared is going to be equal to this thing we call the determinant. So in order to find a solution to this system of equations, you have to rearrange the elements of the matrix and then divide them by the determinant. And that's why it's important that the determinant does not equal 0. If the determinant equals 0, then this system of equations has no solution, because as we know, you cannot divide by 0. So that's where this whole thing comes from. And it's a great exercise if you want to try it by yourself. Just assume that the determinant is not 0, and then start dividing and working around with these elements. Is kind of some nasty algebra, but the thing works out. And so that's why we need that the determinant is not equal to 0, and that we have to solve the system of equations. So if you want to dive deeper into that, there's great videos talking about what the determinant means. If you're still a little bit on the fence about this explanation, I mean, this explanation proves why the determinant cannot be 0, but it's still not as intuitive as we would like. So bear with me while I give you a little brief explanation of the geometrical intuition of why the determinant cannot be 0. Okay, so this may help you get some more intuition about why the determinant matters. So here we have two matrices, 1, 0, 2, 1, and 1, 2, 2, 4. Now, if you've done some linear algebra before, you can clearly see that this matrix is what we call linearly dependent, because the second column is just the first column multiplied by 2 on every of its element, each one of its elements. So what we're going to do with the matrices is we're going to create a parallelogram with the elements here and with the origin. So I wrote here kind of the formula of all of the vertices of this parallelogram, and we're just going to combine them together. So we're going to link this here, going to link this here, link this here, and link this here, right? And you get a very nice shape. So what's the deal with this shape? Well, the thing is that this geometrical figure has what we call area, right? It's occupying some space in a two-dimensional space, right? There's something inside of all of the lines that are being connected. There's something in the interior of this parallelogram. And this is connected to the determinant. In a way, the determinant represents the area that this parallelogram occupies in a two-dimensional space. So if you get a determinant that's positive or negative, rather if it's negative, it just means that it's in a different direction. But if you get a determinant that's different from 0, you're basically saying, hey, this thing is occupying some space. So it's saying that implicitly, it's saying that the matrix represents certain transformation on the space that can be reversed. But let's see what happens if we try to join the dots here and try to make a parallelogram. So we're going to combine 0 with 1, 2. We're going to combine 1, 2 with 2, 4. And then this one should be connected. And then the last step is going to be to connect a plus c, which is going to be 3, with in the x-axis, and b plus d, which is going to be 2 plus 4 in the y-axis, 6. And then we have that. This is not very straight because of my handwriting, but this is just a straight line. And the main difference here, this matrix has a determinant of 0, you can verify that, is that when you have a determinant of 0, you're just looking at a line. You're not looking at something that has area or volume if you're looking at higher dimensions. So when you plot your matrix and you see something that's like a line, you know that there's no area. And therefore, the transformation that this matrix is doing cannot be reversed. That means that there's no inverse. Now, I'm hand waving a lot of details, and maybe this is not going as thoroughly as you would like. Again, there's a lot of great videos that go in depth about this thing. But just so you know, if you want to visualize why this thing has no inverse, then this is the main explanation. Okay, so after we went through all of that, let's just dive in and write our code. So the way I'm going to do this is first calculate the determinant. If the determinant's not, it's 0, then we're just going to stop. And if not, then we're going to apply the formula that we already saw. So let's first calculate the determinant. As we saw, the determinant is AB minus BC, which is first element or element in row 0, column 0, multiplied by element in row 1, column 1. So let's first write that down. Times matrix 1, 1 minus B, which is the element in row 0, column 1, multiplied by C, which is the element in row 1, column 0. And that's going to be the determinant. And we have to check that the determinant is not 0. And in Python, you can do that by saying if not that, which is the value. And if so, we can just return, or we can raise, let's call it a value error. And we can say something like determinant must not be 0. Okay, so if we move out to the next part of the code, then that means that the determinant's not 0. And so we can just simply apply our formula, which, in case you need a refresher, is right here, which simply is going to create a new matrix with the elements flipped as we want them to, and it's just going to be every element is going to have to be divided by the determinant. So this is going to have, again, 2 rows, 2 columns. So the first element is going to be D, which is matrix 1, 1 divided by that. The second element is going to be minus b, which is matrix 0, 1 divided by that. And then we're going to have minus matrix 1, 0, which is c divided by that. And then finally, matrix 0, 0 divided by that, which is a. And here we're dividing every single element by the determinant. You could have done some different method just to multiply everything by 1 over the determinant. But with this, we're going to have our solution and implementation. So let's submit the code. And as we can see, it's accepted and this works. So it's basically doing what we were talking about. Okay, now that we did that, let's go and do something a bit more elaborate. And that's going to be the NumPy one-liner. So let's import NumPy. And NumPy has this amazing module that does linear algebra, which we're going to leverage. So instead of getting the determinant and everything, which NumPy does under the hood, we can just call np.linalg, the aptly named module for linear algebra. There's a formula called imb, and then this is going to have to receive as an input a NumPy array. And what we have as an input is a list of lists. So we have to cast that into a NumPy array. And we do that by calling np.array matrix. And with that, we're going to do the exact same thing, just faster. And as you can see, it works pretty well and the code is accepted. So this is what you're going to be doing if you're running a project or you're trying to do something in production. This is going to be way faster underneath the hood. But well, it's not going to have much of a difference for a 2x2 matrix, but if you're working with higher dimensions, trust me that this is going to be way faster. So there it is. I hope you like this video. Again, there's a lot of heavy involvement of linear algebra in this video and what's happening underneath the hood. I hope that I can at least give you some intuition. And there's a lot of great resources out there to learn more about it. So happy coding and I hope to see you in the next video.